All right. Hi, I'm Logan Longacre. This is my presentation over a weather forecast and how meteorologists can use the singular value decomposition in order to improve their forecasting. So we can begin with the satellite scan. This is taken by the GOES-16 satellite. This is an infrared scan, so it shows a lot of what the human eye can't see. To start off, we have this large empty area that stretches from western Kansas all the way out to the Atlantic Ocean. This is indicative of a high pressure system, also known as an anticyclone. This is characterized by clear weather, nice days, basically. The air is trying to evacuate that area to get to a low pressure system because the atmosphere deep down all it wants is equilibrium. So we can go ahead, outline this, throw an H on it. Oops. Throw an H on it for high pressure system. This will be a mostly clear area. And then down to the south, we have a low pressure system. You can tell because the clouds are converging there. They have sort of a cyclonic bend to them, which just means counterclockwise, at least in the northern hemisphere. And these will be where the fun, quote unquote, depending on who you are and how you interpret it, weather occurs. This will just mostly be cloudy, gray, rainy, that kind of thing. So we can go ahead and put an L on it. Oops. And then we can take a look at professional analysis. It's still subjective, but it's by a professional who's smarter than me. And take a look at what they thought. They mostly agree with what I said. They have highs in all the same areas as I do. They have a low in the same area as I do. So I would say that's pretty good. I can at least read a satellite scan. So where do we want to forecast? Let's go ahead and do somewhere close to home. So let's sort of zoom in on this area. This is now a visible scan. We have a pretty broad area right here of cumulus clouds. These are caused by daytime convection, which is just the sun heating the surface and causing air to rise. This exact formation is called a cloud street. You can tell there's like a xylophone kind of pattern to it. There's a bunch of strips. That's caused by uneven heating. And it forms sort of parallel to the winds. So we can imagine that the winds are sort of coming from the southwest. And then there's also this broad area of wispy cirriform clouds. These are high in the atmosphere, very thin, don't really have an effect on the weather. They're too thin to prevent sunlight from reaching the surface. They're just there. So where do we want to exactly forecast? We can go ahead and choose this area right here. This is around Omaha, Nebraska. So validation and climatology, I will use Omaha. So we can take a look at this. It's called a sounding. It shows the profile of the weather through a column of air. Get it from a weather balloon. So down to the surface, we have 80 degrees Fahrenheit, which is around 27 degrees Celsius. 10 knot winds out of the southwest, lines up with what I said about the clouds, which is around 12 miles an hour, 17 kilometers an hour. And then we can also use this chart to tell where the clouds were on that previous slide. So where the dew point, which is the green line, and the red line, which is the temperature, come together, that's likely where the clouds formed. So we can go ahead and isolate that through our image of the clouds, just as a reminder. That's around 625 millibars, which for this set of conditions, we can use the hypsometric relation, which relates the pressure and the temperature to the height of a layer. So for this exact layer and the temperature, it's around 3,600 meters or 2.29 miles. So just a little neat thing we can do. It's around 3 miles in the atmosphere. So what's pertinent? We want to know how these conditions evolve from the current time until midnight. So what would change just nighttime cooling is if there was a layer of clouds like this, because normally at night energy leaves the surface and it goes out to space, but when it's cloudy, these clouds reflect it and trap it in the atmosphere like the greenhouse effect. It's not like it is the greenhouse effect, which would cause a warm, probably pretty stuffy night. Because those cumulus clouds are probably pretty evanescent, they're probably not going to stick around for a long time. We can assume that that's not the case. We can assume that that energy is going to go straight out to space and the Earth is going to cool as normal. So we can also use climatology in order to assist us with what that temperature will actually be. So for an 80-degree day, this isn't a precise science, but for an 80-degree day, the low temperature is generally around 60 degrees. So we can go ahead and say that by midnight, the temperature will be around 60 degrees. And then also we can assume that the wind is going to weaken a little bit, probably down to around like 5 knots, because the pressure gradient relaxes at night, and that's the main driving force behind the wind. As I said before, wind wants to go, or air wants to go from a high pressure to a low pressure, and that's what wind is. It's that air leaving the high pressure to go to the low pressure. So we can now look at a simulated sounding. This is using the NAM model, the North American model. It says, I did a pretty good job. 60 degrees down at the surface, which is around 17 degrees Celsius, I believe. And then our wind is now around 5 knots, so it's still pretty weak. Did a decent job on it. So our absolute error, 1 degree Fahrenheit, 1/4 of a mile an hour. Relative error, 0.017 for the temperature and 0.13 for the wind. Pretty good. Just threw that in to tie it back to linear algebra a little bit. Sort of get us thinking about class. So now I'll sort of shift the discussion to how meteorologists can use singular value decomposition to improve their forecasts. So this image probably seems a little bit familiar. You might recognize it. Here's a comparison. This image is from the European Center for Mid-Range Weather Forecasting. This is training regarding one of their models. And this is exactly what happens when we employ the SVD. We start off with the vector V, or the matrix V, apply sigma to it, and then we apply U to it, and then it creates that hyperellipse right there. Just to further drive home the comparison, here's my notes from when Dr. Miedlar taught us about it. Mine are pretty bad, but you can see, starts off with a circle, ends up down with a hyperellipse. Pretty nice way to see the application. So, and then a specific SVD-based model in particular is the EPS, which is the Ensemble Prediction System. It is the training, or it is what this training slide is about. It's from the ECMWF. Excuse me, my apologies. It uses an ensemble of 51 forecasts to create a more accurate base image of the atmosphere. It's impossible for us to know what the exact state of the atmosphere at any given time is. Physically, metaphysically, metaphorically, philosophically, it's impossible for us to know it in all those ways. So, what is special about these 51 forecast initial states? We have one base state, which is the original approximation of the atmosphere, and then the 50 others are just slight variations on it in order to give us this analysis all the way over here that I can barely reach. In order to narrow the distance between the dots in the forecast panel. So essentially what we want to do with those SVDs, or those singular vectors, my apologies, is to reduce the forecast error. And that's exactly the goal of the EPS and ensemble forecast systems in general. So, okay. So in order for ensemble systems to be valid, they have to assume that the fastest growing initial errors are responsible for a majority of the forecast uncertainty. Those are identified with the first vector in our matrix V, the leading vector. And then we use singular values in order to determine which of those perturbations leads to that great uncertainty. So in short, singular vectors are used by meteorologists to constrain the error inherent to forecasting. So I leave you with a very long quote from Pierre-Simon Laplace, French mathematician and philosopher. That's definitely a name that's familiar to most of us from all of our fields of math. What he's essentially saying, he's proposing an omniscient being which knows the position and momentum of every single particle in the universe, and with that, it can predict the future of the universe, which is essentially what we're trying to do. We will definitely never be able to replicate that. It's called the Laplacian demon. It's a nice thought experiment, and that is what I leave you with. Thank you.